Dr. Beck, and today I'm going to talk with you about electronegativity. Ultimately, we're going to use this to be able to figure out the polarity of bonds and polarity of molecules. And after today, we'll be able to use this as we look at Lewis structures and ultimately three-dimensional structures of molecules. Electronegativity is an important concept, so let's make sure we have it down. Okay, we define electronegativity as the ability of atoms in a molecule to attract electrons to themselves. And so we're looking at individual atoms, so every atom is going to have some ability to draw an electron to itself. This is similar to the idea of electron affinity, but electronegativity has to do with atoms that are stuck together in a single molecule. Electron affinity is an atom all by itself, with the ability to draw an electron to itself. Here we're looking at those atoms that are in a molecule, so they're sharing electrons. Okay, let's take a simplistic model. So if we think of a bond as being simply a sharing of electrons, so electrons that exist between two atoms, we can think of it conceptually as something like this, where we have two atoms, a blue one and a pink one. They have some protons that are sitting in the nucleus, and of course those protons are what hold those electrons together and hold things into one molecule. And they're sharing some electrons, so there are electrons that are sitting, in this case, right between them. And those electrons are existing in some sort of cloud, so there's a propensity, there's a likelihood of finding those electrons. Most often we'll find them sit between these two. So this is an equal sharing of electrons. So we have the same amount of charge and the same distance between charges, and those electrons are being equally drawn to each of those two nuclei. And we can look at this in more sophisticated ways, so we can look at this in a three-dimensional view. So suppose we have two fluorine atoms that are bound together, this bond indicating the sharing of two electrons. And what this looks like on the surface is something like this. This shows that those electrons are going to be drawn into the nucleus while at the same time being repelled from each other. And it'll end up having some surface charge that gets spread all around. So we have electrons on the surface of molecules that get spread all over the surface of a molecule. And because we have two equally charged centers, we have two equal atoms, that charge gets distributed all the way across the entire molecule quite evenly. All right, well, let's look at what happens when we don't have equal charge that exists. Suppose that we have more of a charge in one atom than another atom. And here I'm keeping the distance the same. I could change the distance as well. But remember from Coulomb's law that the increase in charge is going to have a bigger effect than a slight change in the distance between the two. So increasing in charge is going to have the biggest effect. Okay, so I increase the charge, and now I have these electrons that are being shared by these two atoms. But now I'm going to have an unequal sharing of those electrons. So electrons will spend more time by the atom that has a higher positive charge and less time by the atom that has a less negative charge. It's still a sharing of electrons, but it's an unequal sharing of electrons. Let's take a quick look at what this looks like on the surface of the molecule. Okay. So we can go change our fluorine molecule into hydrogen fluoride. So hydrogen is very small, +1 charge. Fluorine is also very small, but has an effective nuclear charge of 7, you may recall. And we can look at what this looks like. So we have a small molecule with a very small molecule with a small nuclear charge of +1 hydrogen, shown here in white. And I have a larger molecule, fluorine, that has a much larger nuclear charge. And what we see on the surface of the molecule is that the electrons will be drawn to that larger charge. So the electrons will spend more time somewhere around the fluorine molecule. Remember, they're moving around. But on average, the electrons will spend more time by the fluorine than they will by the hydrogen. The net result is going to be that on the surface, we'll have a more negative charge by the fluorine and a more positive charge that's going to exist by the hydrogen atom in this molecule. And this is what electronegativity is going to look like. So electronegativity is going to be the difference between the attraction of the two. So if we have equal attraction, we'll have a strong covalent bond, and we'll have no net charge on the surface. The surface will be the same everywhere on the molecule. If we have a significant difference in electronegativity, we'll have a surface charge that will be distributed unevenly, meaning one side of the bond, one side of the shared electrons is going to be more negative than the other side. Okay. Electronegativity is a characteristic of all atoms, and we can plot out what are the electronegativity values for every single atom in the periodic table. And it looks something like this. You'll notice a few trends here. So as we go across the periodic table, electronegativity increases. We think of this in two ways, right? This is still all based off of Coulomb's law. So the charge and the distance are the two things that are affecting this. The attraction of the electrons between the charge and the distance. As we go across the periodic table, remember our atoms are getting smaller and our effective nuclear charge is increasing. So as we go across the periodic table, we would anticipate that we'd have higher effective nuclear charge, be able to draw those electrons to them, and it's smaller, so the distance between the shared electrons and the nucleus is going to be shorter, so that would increase the attraction as well. Second trend that you see is that as you go down the periodic table, that the electronegativity decreases. Remember, as we go down the periodic table, we're going out in energy levels. So our distance from the nucleus to the outermost electrons is going to be increasing. So we can plot the difference in electronegativity. So if we look at any two atoms and the bond or the interaction between the sharing of electrons that might occur there, and we can find there'll be any spectrum of differences of electronegativity values. And we're going to estimate that everything that's greater than a difference of 2.0, we're going to call ionic. So the electrons are shared so infrequently that they've just been transferred. If we have something that have the same electronegativity value, the difference is going to be 0. So these would be entirely covalent bonds, so actually shared, and we'll call it nonpolar. The electrons are shared equally. And there's all sorts of stuff in between. And as we looked at the example of hydrogen fluoride, that we can have something that will be very, very unequal sharing of electrons, but still less than electronegativity difference of 2. So we consider it covalent bond. So there's still sharing of electrons, but it's a very unequal sharing of electrons. We're going to represent this unequal sharing with these little delta signs. So we'll have a delta negative that tells us there's a slight negative charge on the surface of the molecule, meaning there are more electrons hanging out of that side than there are protons to compensate for that. And we have a slightly positive side, delta positive side, where we have a deficit of electrons in comparison to protons. Okay, so let's take a look at what this might look like. So here's a molecule you might recognize. I have oxygen and hydrogen bonds. I happen to have 2 of them, but we'll work with each one separately. So I have 2 atoms. I have oxygen, hydrogen. Oxygen has electronegativity of 3.5. Hydrogen has electronegativity of 2.1. The difference in electronegativity is going to be 1.4, so it's less than 2, which means this will be a sharing of electrons. We know this is going to be a covalent bond, but it's an unequal sharing of electrons. So we're going to represent this unequal sharing of electrons by putting little delta signs in here. So we have a slightly negative charge on the oxygen side of the oxygen-hydrogen bond. A slightly positive charge is going to be on the hydrogen side. Right, guys, we're going to have 2 of these. We'll have the same on the second side. So for the second bond, we're going to have a slightly negative charge and a slightly positive charge. And we're going to represent this, say, well, we have some bonds that are polar. So this is unequal sharing. So the electrons are going to be more on one side than another side. We can represent the 2 bonds by saying these are polar. We'll draw arrows going from the positive side to the negative side. So this is my polar bond that's going to exist. We'll want to take a look at the molecule, and here we're going to want to take the vector sum of these 2 arrows. So we're going to add these 2 arrows together, and we're going to end up with some sort of resultant vector. It's going to look like this. We're just going to say this is the sum of those 2 arrows, and overall, my molecule is going to be polar, and we're going to represent this polarity of the molecule. So dipole moment is going to be a single arrow, which represents the molecule and the polarity of that molecule. All right, now let's look at another example. So here we have carbon dioxide. It happens to have double bonds, but it makes no difference. We have 2 atoms that are sharing electrons. They happen to be sharing more electrons. The carbon and oxygen bonds are going to be sharing electrons on either side. So we can calculate the electronegativity difference between carbon and oxygen. Oxygen 3.5, carbon's 2.5, so electronegativity difference of 1.0. So on our carbon-oxygen bond, we're going to have a polar bond, meaning the electrons are going to hang out, in this case, more at the oxygen side than they will at the carbon side. We'll also have another polar bond between the other oxygen-carbon. So we have 2 polar bonds. We can represent this with arrows, as we did previously with water. And we'll have 2 polar bonds in this molecule. Notice that due to the geometric arrangement of these carbon and oxygens, that these arrows, when we add them together, will cancel out. In this case, we have a molecule that has two polar bonds, but it's not a polar molecule. So overall, the molecule doesn't have a distribution of electrons that differs on the surface. There is not a net positive charge or a net negative charge anywhere on the surface of this molecule, despite the fact that we have unequal sharing of electrons that happens deep down inside in the bonding level. Okay, briefly, let me make a few distinctions. So previously, we've talked about how to characterize electrons and the movement of electrons in individual atoms. We've spoken about ionization energies, so the ability to take an electron and take it off of an atom. And we've done the reverse. We've talked about electron affinity, so if we add an electron into a single atom. Please remember, these are individual atoms, so atoms sitting all by themselves in the gaseous phase. They're not interacting with any other atoms. We've looked at compounds, where we stick atoms next to each other, and two things can happen. We can have an ionic compound. We talked previously about lattice energy, how to characterize the energy that holds those ionic atoms together. Or we can have a covalent compound. Covalent compound, we use electronegativity as a measure of how those electrons are drawn to each atom within the molecule. And this can lead us to predict polarity. An important distinction to make: you can have polar bonds but not have a polar molecule. And we'll use this a little bit more as we get to draw Lewis structures, which is coming up next. Thank you.